Reverse emulation. If you've been following my channel, you know that I like to do projects about the Nintendo. I also like to do projects that are kind of humorous and sort of technically humorous. So we're going to do one of those. We're going to tell a joke. I'm going to tell a joke to you. And before we do that, though, I think this joke works better if we start and we do it inside out. So first I want to start by talking about what is funny. And of course, lots of pretentious people even more pretentious than me, have studied this problem and thereby desiccated it into a kind of dry prune dust for hundreds of years. But bear with me for a second. So some old-timey guy says that if you show me a movie of a man eating a boot and this person is sweating and has a look of disgust on their face, that's not funny. But on the other hand, if you show me a movie of someone with a distinguished look on their face and a neutral facial expression eating a boot, that is funny. Now, I don't think either of these things are funny. Maybe it's meta-funny that once upon a time, eating boots was considered the apex of slapstick humor. But there is something to this, and it's the idea that if I violate your expectations, humor can be found there. Let's do a couple more of these, and I want to get to a technical joke. So Mario eating a boot, that's not funny. Here the joke is, oh, I saw Super Mario. It's like retro. I don't think that is in and of itself funny. On the other hand, Samus eating Tide Pods, at least in the year 1986, is potentially funny because Tide Pods didn't exist in 1986, and so that's anachronism. One more. Self-reference. Now we're really talking about technical jokes. I think self-reference or recursion is a really good way to find humor, but actually not all self-reference is humorous. For example, if I tell you, my name is Tom Seven, that's not inherently funny. On the other hand, I do think inherently funny is this notion of strange loops, and this is due to Douglas Hofstadter. Here's a great example of a strange loop. It's a quine. I didn't invent this. This predates even my birth. The top there is source code that I have split onto multiple lines, but if it were all one line, then if I pass that into a compiler, it produces a program, and if I run that program, it spits out the same exact source code that was its own source code, and that's amazing. This is one of the best technical jokes that I know. However, I contend that the fact that this is a loop is not as important as that last step. That last step is where the magic is really happening, because here we normally think of source code as a precursor to a program, because after all, the source code is what forms the program. But here you have a program printing out source code. And so that last step violates my expectation of sort of the order in which source code and programs come. So enter improper hierarchy. And this is the kind of joke that I'm going to tell you today. Basically, if you have some kind of expectation of a hierarchy or a sequence, and you do that in the wrong way, then that's improper hierarchy. I just made that up. As an example, past, present, future, well, the past is sort of part of the present as our memories. But if I take something from the present and put it into the past, that's anachronism. That's an example of improper hierarchy. And just to really beat this one to death, self-reference contains strange loops as a Venn diagram, but improper hierarchy is a generalization of strange loops that don't necessarily have to be loops. And here's a pro tip for you if you're trying to self-promote. Manage to get yourself on a slide with Descartes and Douglas Hofstadter and have it make sense. Draw that specious parallel, and then no one can stop you. So we're going to do a joke about improper hierarchy, but in order to do that, first we need to take a look at the Nintendo motherboard. Here's a drawing of it. On the left you have the CPU. That's an old 8-bit microprocessor that runs about 1.7 megahertz. And on the right, you have the PPU. That's like the graphics chip of the Nintendo. That runs a bit faster, but it's not programmable. Then there's this asshole. This copyright chip, its only job is to reset your Nintendo if it senses that something is amiss. And so actually, you're probably familiar with the meme of blowing in a Nintendo cartridge. This does nothing and is actually probably bad for your cartridges. The only thing that will cause your Nintendo to reset itself and blink that light is this stupid chip. So thanks a lot, Nintendo. They put that there on purpose. Now, the CPU and PPU talk to a cartridge. The cartridge is the dual of the Nintendo. This one's called Footballs, actually formerly known as a game pack. And if you open up a game pack, which you paid $60 for in the 1980s money, you'll find this hilariously small circuit board. And it has two chips on it. One of them is for the CPU. That's the ROM, read-only memory, which contains the program for the CPU. And one of them is the PPU, ROM, which contains graphics for graphics. There's also a counterpart of the CIC that prevents it from resetting. You'll also notice a huge amount of space in here. Of course, the Japanese version of this, the Famicom, those cartridges are like the right size for this little circuit board. But when we imported this in the United States, we were like, you know, USA #1, and made the SUV of cartridges. But that's going to come in handy. This gives me an idea. So here's the normal setup. You have the Nintendo hardware and you have a game. And emulation, which you're familiar with, I think, is where I take the hardware and I toss that in the trash and I replace that with software. So I implement sort of the chips that are on the Nintendo in software, and then I can load a game into that as a file and play it on my computer, which is great. So here's the idea. Reverse emulation. I'm going to flip this on its head. So what if instead I keep the hardware around and I don't modify it, but I take the cartridge and those ROMs, what if I replace those ROMs with something a lot more fancy than ROM? Normally a ROM is just this read-only thing that contains some data, and it's a very sort of dumb device. All you can do is look up data within it. But if I replace that with something really fancy, I think I can make the Nintendo do things that it would otherwise be incapable of doing. So this is the Raspberry Pi Zero W. It's a tiny computer that costs $10. It has wireless and it has a 1 gigahertz CPU and a lot of memory. It's a pretty amazing thing to cost $10, and it's pretty small. So my fantasy, this is a fantasy schematic, is that I should be able to just hook up that thing. It's a modern device, so I imagine it's like so much faster than the Nintendo. I'm used to that being the case. For example, the emulator that I'm working on can run Nintendo about 28,000 frames per second. And so, you know, that's orders of magnitude faster than a real Nintendo. I'll just hook that thing up to the very slow Nintendo, and I'll read addresses as they're requested from the ROM, and then I'll supply data, but in between I'll be able to do a whole bunch of computation and produce interesting phenomenon. Of course, I'll need some resistor or something. I'm not totally naive about this. Well, we'll see. Now, one thing that gave me hope is I flipped over the Nintendo to inspect its vulnerable underbelly, and I saw these stickers, and one of them says, blah, 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 FCC compliant. This device may not cause harmful interference, and this device must accept any interference that may be received, including interference that may cause undesired operation. So basically, this behavior is required by law, so it has to work. And in case it hasn't become clear to you yet, this entire video, and the reason why it is so strange, is because I'm doing this video on an actual unmodified Nintendo. So let me adjust the camera there so you can see that. And I'm changing the slides with the Nintendo controller, of course. So that's kind of like Nintendo PowerPoint. All right, let's talk about how this works. The Nintendo's graphics are present through two tables. It's not that important, but basically there are these tiles that are used over and over again on the screen, and they're 8 by 8 pixels each. And so a screen of Super Mario is basically made up of these tiles on this grid, as seen here. Separate from the tiles, there's a region of memory called the attributes, which let you set colors to regions of the screen. And there's basically 13 colors that you have access to in 4 different palettes. These are all of the colors that the Nintendo can display total, but I can't put them all on screen at once because we are actually using a Nintendo, and it has this limitation where you can only have 13 active at once. Now, the region of a screen that can be given a color is larger than an individual tile. It's the size of that question mark block, and this is why Nintendo graphics usually come in that scale. Also, we've talked about this before, but I just love that the cloud and the bush have the same actual graphics, just with different colors. So we just talked about one serious limitation that the Nintendo apparently has, which is this color resolution. It can only render a 16 by 16 square region with one of 4 colors because I select one of the 4 palettes. But if you look at how the Nintendo actually renders, it doesn't work this way. It doesn't render that whole thing all at once. It renders it in 8 by 1 strips, 8 pixels by 1 pixel. And in fact, it reads the color every time it renders one of those strips. So if I'm reverse emulating the ROM and I'm able to supply a different value every time it reads the same address, I can change the color as often as I want for each one of those strips. So this doesn't totally get around the color limitations, of course, but it does allow the Nintendo to access functionality that it doesn't apparently have, but it does in fact have, because this is an unmodified Nintendo. It just needed to believe in itself. Another such limitation is update speed. So normally it's rendering scan lines, 240 of those, and then it enters this period of v-blank. And during scanline rendering, you can't access the PPU, the graphics processor, because it would cause terrible glitches. So you can only be updating the screen for about 1/13 of the entire frame, and you have to do so over a fairly slow connection between the CPU and the PPU. And so the upshot of this is that if I look at Mario, for example, only about this much of the screen can be updated per frame. And so there's sort of an absolute limit to how fast Mario could even move, because I wouldn't be able to draw the level fast enough to catch up with him if he was moving faster. But because I'm reverse emulating the graphics, I can update every tile as often as I want, which means that I can do, for example, full motion video. Here showing you a classic. Don't worry, this isn't the joke. But it is, I don't know, it looks pretty good, I think. Maybe the best graphics as yet seen on the Nintendo. So I made a whole separate video describing the technical details for this, and please watch that if you're interested in it. But I want to give you a little bit of a sense of how much work goes into pulling a trick like this. So here is an oscilloscope image of the Nintendo, some of the wires on the Nintendo, actually this Nintendo. And I took, in fact, this image and I put it inside the cartridge, which it's then being converted into the signals to send over those very same wires in order to produce graphics, which I think is kind of amazing. An example of improper hierarchy, if not a strange loop. Anyway, that thing at the top is a timing signal that the PPU uses to tell the ROM that it'd like to read from it. And you'll note that these are measured in nanoseconds, so it's pretty fast. Then there's 16 addresses that come in. That's like, which address would you like to read? And there's 8 data bits that go out from the ROM. So I wondered, how fast can the Raspberry Pi keep up with this? And the answer is this. It's only about 3 times faster than the PPU ROM. And that's kind of bad, actually. Like, I'm used to this being tens of thousands of times faster. For example, the emulator I'm working on right now can do 28,000 Nintendo frames per second on my desktop. So this was cutting it close. And actually, you know, that's the bandwidth. If I take latency into account, it turns out it just doesn't work. If I do the most basic thing, hand-optimized assembly, and I just read an address and then return the byte, so that's like what a ROM normally does, the pulse comes out late and doesn't work. It doesn't arrive in time for the Nintendo to read it. So I use a trick, and this is a good one. You know, if you can't submit your paper on time to the conference, just submit on time for next year's deadline. So as soon as the read cycle, actually as soon as the wait cycle begins, I immediately write the data. And then that means that, taking into account the latency, it arrives barely on time, and that works. Then I'm free to read the addresses. Now this is cool and it works, except that now, of course, my read happens after my write, so that means that my write can't depend on the address that was read, which is a problem. So what my software is actually doing is predicting what will be the next byte that the PPU wants, and sending that as soon as the cycle begins, and then updating its guess about where it is on the screen based on the addresses that are read. And the PPU is pretty predictable, so this works okay. But this is the main reason why you see noise and jank on the screen. That's a hard problem to tame, and I didn't do it completely. Of course, those signals are not actually nice square waves. Digital is not real. They actually look like this in the analog domain. And so there's a lot of work in making hardware in addition to that software to support this. So here's the board, the schematic that I created in the layout. You can see that's much more complicated than my fantasy schematic. And here it is actually installed in a cartridge with the Raspberry Pi soldered onto it. You'll see upstairs the CIC chip, which I have to harvest from a Nintendo game, because they don't sell those, and I need it, otherwise the Nintendo will reject my cartridge. So that kind of stinks, because I have to desolder those from real Nintendo games, which breaks my heart a little bit. And also, Nintendo games are getting kind of expensive. These are 30-year-old cartridges, and now like the cheapest Nintendo games, if you want to buy them just for their chips, are getting to be more expensive than the cheapest Super Nintendo games, which seems like an inversion to me. This big chip here is actually a ROM that I created for the CPU side. This was the program that runs. The rest is concerned with the graphics, but I do need to do some stuff with the CPU. So one thing is I want to be able to set the palette before each frame starts, pick the 13 of the 64 colors that I'm going to use for that frame. I'm also going to be able to read the input so that I can control the slides. So here's how that works. Normally the PPU is communicating with this board during scan lines, is reading, and the board is supplying data, and the CPU is idle. But then when VBlank begins, it gets an interrupt and wakes up. And now the CPU is going to communicate with the board because it can also read from graphics memory, and it's only going to use reads in order to do this. Here's what it looks like. So I do a sequence of reads, but I do these reads in descending order because the PPU never actually renders from right to left, always goes from left to right. And so as I'm doing these reads, the board is able to recognize that it's talking to the CPU and not the PPU because of the strange sequence of reads, and I call this knocking. Once it's synchronized, now the addresses don't matter, and I can send it the CPU data because I know I'm not talking to the screen, and so I won't be messing up the graphics. That's how I send the palette, and then the CPU can install it. So that's mission accomplished for installing the palette. How do I get the controllers? Well, this is really the same trick. The CPU reads the controllers. There's 8 bits on a controller because there's 8 buttons. And we normally think of a read as being a one-way thing, but actually in order to do a read, I need to tell the quote-unquote ROM the address that it would like to read, and I get back data. So because the addresses don't matter once I'm synced up, I can actually put the joystick bits inside the addresses that I read, and then the board can read those out of the addresses, and it can know what the player is doing on the controllers, which is great. So I can switch slides. Unfortunately, this whole process uses up 2/3 of VBlank. As I mentioned, it's a fairly slow thing. And this only leaves me with half a millisecond in order to do anything interesting, which is really not enough. I can run some animations and I can, switch slides. So I upgraded to a fancier Raspberry Pi, which has 4 cores. And this is going to let me do something on the other cores while I'm rendering on the main one. And so let's switch to that cartridge right now. Okay, so let's do this. Here I have another cartridge, and this is using a Raspberry Pi 3. It doesn't exactly fit within the cartridge, but it still fits within the Nintendo. A little bit of finesse. Okay, power that up, and I'll show you the debugging view as it boots. I'm going through some trouble for continuity here, so no one can accuse me of cheating, faking it. What's different about this machine? So this has a 4-core processor, and that's going to allow me to do some computation, not just in VBlank, but while the other core is running. There's a problem here, which is that Linux is going to continue to interrupt me, and that's going to cause it to blink like this. But other than that, I'm pretty happy with how this came out. So here we are with my joke. In case you're not brushed up on your Nintendo, this is Super Mario World, the launch title for the Super Nintendo, a 16-bit console that came out years after the Nintendo. And, you shouldn't be able to play Super Mario World with its advanced graphics on an unmodified Nintendo. Putting aside the janky noise and the blinking, it works, and I can play it because I've also arranged for my controller to pass through. And actually, coincidentally, the controller, I only have 8 buttons on this thing, right? I don't have all of the buttons on a Super Nintendo, but somehow like up on the Nintendo is the same bit as up on the Super Nintendo, which is like a cosmic coincidence, or perhaps they just, got lazy. So let's play this game for a second. So I can only do a spin jump because I have run and I have spin jump, but none of the other, I can't do a normal jump, which makes it a little harder. But I know how to spin jump. Played this level a lot of times. So what else is going on here? Well, one thing I'm doing is I'm modulating the scroll offset on the Nintendo, but also sort of unscrolling the screen by 4 pixels every other frame. What that lets me do, okay, just got me by the teeth there. What that lets me do is avoid some of the blockiness. So you know how I have to do sort of 8x1, 8x1 strips. I can put those 8x1 strips on a different grid every other frame, which eliminates some of the blockiness. I think that helps with the color resolution a bit. Okay, so you don't need to watch me play that. Another thing I can do is play regular Mario. So here, of course, I have a Nintendo emulator inside the Raspberry Pi, inside that cartridge, and I can take the graphics that come out of that and pipe them through to the real Nintendo, which then can display them with all of the graphical problems that entails. Oh yeah, people hate it when I mess that one up. I love trolling them. So I think this is a nice joke. It's elegant how it forms a loop, but honestly, I think that the Super Nintendo on Nintendo is a better joke, and that's where I was going with all that stuff about improper hierarchy. So I guess let me know which one you liked better. But let's get back to Nintendo PowerPoint for a wrap-up. So one more thought before I leave you. This technology is good for enhancing nostalgic hardware like the Nintendo, the Super Nintendo, Nintendo 64, GameCube, and maybe, I don't know, the human brain. That's something I feel nostalgia for. And I think about artificial intelligence, it seems evident to me that we will eventually succeed at this. And I worry a little bit about that. Not just because we might destroy ourselves and destroy society, but because of the feeling of being left behind. We already have, for example, chess computers that it's not even fun to play against because they're so much better than us. So one of the things I like about this project, even though it's really just a lark, is that it tells me a little bit about what it might feel like if we were to reverse emulate the human brain. Now, I'm not talking about emulation. That's like uploading your brain into the cloud or something. I'm talking about replacing parts of your hardware, parts of your brain, with technology that surpasses your brain in functionality. So for example, we could imagine replacing our memories, or the hardware that powers our memories, if that is a place and if it's possible to interface with computers, which maybe, we could imagine replacing that. And that might allow us to feel much more powerful and smart than we would normally be. So let's say, for example, I wanted to know what are the prime factors of this number. That's a pretty boring example. But it's a good example of a thing a computer is good at and people are very bad at. So I might ask myself this question, and then I might recall knowing the answer, perhaps by repeating some kind of rote fact. For example, I might go A, B, C, D, but then my memory, which is powered by some kind of advanced future thing, could then complete that with the answer to the problem, 472866029, blah, blah, blah. We might want to also trick the brain into thinking that it rhymes, because it's not very satisfying when it's not the right length. So that's kind of a cool idea. And, it might end up, one day we might end up making it work that way. Although I think that the alphabet is kind of useful, so I'd prefer to remember it. But I realize I have all of these memories that I don't care about. So what if instead it was something like, oh, you remember that time when in Charles in Charge, Charles needed to factorize that number and the answer was blah, 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 blah? That I think would be actually a pretty acceptable technology. Sign me up. So that's all I've got for you. Thanks for paying attention, and if you liked it, subscribe or do what one does. Thanks.